Alright.
Today we are gonna work on two examples on buckling, and then we finish the columns. And on Wednesday we are gonna start chapter 4, which is about failure theory. But we are gonna have a short review on Wednesday about properties of the material.
Dr. Goffey, will there be any in-class review for the test at all, or?
No, I just posted
Just the study guide sheet?
yes.
Okay.
But if you have any questions, you can.
What are we allowed to bring to the test?
Bring calculator, it's open book and open doc.
Oh yeah, do we need to have drafting stuff?
Yes, thanks. So for the most weekend, yes. Thank you. Yeah, drafting instrument for the most weekend.
How many questions
Level 3. It depends. I have not designed the exam yet, but
It only costs about $1.12
or maybe 4 short. Alright, let me first write it down, whatever we covered or derived on columns. Then I'm going to work on one important example. For Euler criteria, this is a critical to find what would be the critical force applied to the column when the buckling is going to start. C is the end condition depending on pin, pin fix, fixed free, or fixed pin. We can pick the C. E is the modular elasticity. I, second moment of area for cross section, and L is the length of column. So the other version of the Euler criteria is going to look like it's going to look like this. They are the same, just this one is the load per unit of area, and K is the radius of gyration. Which is A equals to I times K squared. This is how we can find K. And the Johnson criteria, before I go through the Johnson, let me introduce L over K1, which is square root of 2 pi squared AC divided by SY. SY yield strength. SY minus this is a Johnson criteria. If L over K is less than L over K1 or equals. And this one is valid when L over K for the column is greater than or equals to L over K1. So these are what we covered.
I have a question.
Sure.
Last week you said that I was equal to AK squared. Is it A equals I K squared? Which one?
My bad. No. I equals to. Thanks for catching.
Thank you.
Yeah. Thank you. So revise this. Any Any other question so far? So we are gonna work on this example. I cannot ask you any more difficult than this problem. So if you know how to work on this problem for the buckling, you should be good. So we have this bar which has been connected to this link. So through this point B is a pin, another pin, point C, and there is another pin at point O. So one force applied here, 800 Newton. So this is the total load applied to this system. So we are gonna design this bar. This wide is 25 millimeter. So and the cross section of this is something like this. If I look from this view, I will see 25 millimeter and this thick. So we are going to design the thickness of bar OB. So it's made of the material with SY equals to 165 megapascal, and the modular elasticity 207 gigapascal. We would like to consider factor of safety equals to 4. So factor of safety should be set equals to 4. So we would like to design this. So first of all, we should find what would be the force. What would be the force applied to bar OB? Then after we figure out what would be the force applied to the OB, if it's compressive, we should check two things: buckling, failure due to the buckling, and failure due to the yielding. But if it was only tensile force, or the bar is under tension, the only thing that we should be worried is the yielding. So in any other problem, the first thing that you need to find if you want to design a mechanical component is the load applied to that specific component. So far so good? Because I'm going to ask you to work on one class activity if this one is here. All right. For this component BAC, draw the free body diagram that we learned from the statics and find the force applied to point B. So if this is find the force applied to point B. If you find the force applied to point B, the reaction of that force is going to apply to bar OB. So then we can find the force. I made a hint just for free body diagram, you need to set the moments about point A equals to 0, because this mechanism is not moving, it's not rotating, so the moment applied to point A should be equals to 0. By setting that, you can find force FP. Is that clear? Before we start, who knows that the direction of force Fp, at which direction force Fp should be applied to point P? Just the line, I mean, I'm not saying that it should go up or down. At which sides it should go?
Which side of it?
I mean, which axis, if I can say?
Yeah, x-axis.
Only x-axis?
Yeah.
It should be this bar. I mean, this system is not moving, so it means any force applied to this should be in the direction of this axis. So FB, either it goes up or down, it should be in this direction with the angle of theta, which is equals to this. This. This angle should be equals to this. So this is FB. So by knowing that, find the force applied to point P. We are looking for FP. After I find FP, I can say the opposite direction is going to apply to bar OB. In exam problem or any other problem that you will see, I expect you know how to find the reaction and the force applied to the components. Then we start the analysis. Number 19. That's you.
I haven't finished yet, but I could get it get started.
Okay, just where should we start?
Do a summation of forces and moments.
Okay.
Since the sum of moments has to be 0, I was starting the summation of moments around point A. So, that's
So
all.
summation of the moment about point A should be equals to 0.
So then, 800 newtons times 7 the angle at C times the distance from A to C should be equal to the force coming from OB times.
What should be the distance?
I hadn't gotten there yet.
I mean, this force, we are looking moment about this point. So this force has the perpendicular distance of 500 from point A. Make sense? So I just need to multiply this by this one because I already could find the projection of this line in x direction. So 500 or 0.5, whatever. And it's making clockwise moment, so it's got to be negative. What would be the second moment?
Yeah, it should be 0.75.
Sorry, I read this one. Thank you. What would 0.75? This distance. I didn't see this. Because this force along this direction doesn't make any moment. What would be the second term of the moment? Which makes the summation of the moment equals to 0.
Be the force multiplied
Okay?
by 0.5.
This force times this, you mean?
Yep.
This force has two projections. One FPX and one FPY.
So the FPX times distance.
So we shouldn't apply this by this because the y projection, the y component doesn't make any moments about point A. So only the FPX times this distance, which is 0.5, and it's making counterclockwise. Set it equals to 0. How can I find FPX? If this is FP, this angle is theta. FP times cosine of theta is going to give me FPX. So negative 800 times 0.75 plus FP cosine of theta equals to times 0.5 equals to 0. So this is how I can find FP. How can I find theta? Theta is this angle or this angle. The tangent of this theta is this length divided by this length. The tangent of theta would be 0.5 times 0.75. Then theta would be the tangent inverse of this, which is 29.05 degrees. So you have theta, you find FD. FD would be 800 times 0.75 divided by 0.5 times cosine of 29.05. You will find FD equals to 1373 Newton. So at point B, this force FP is going to apply here with the magnitude of 1373. Any question on this? As an engineer, this is a very important part for you to find the force and loads applied to the mechanical components. because this is the first step to start doing the analysis. I can guarantee that I'm going to ask something like this, not on buckling, on the exam to find the loads applied to the specific point, and I assume that you should know how to do it. Yes.
Shouldn't the tangent instead of be 0.5 over 0.9?
Thank you. I had 0.9, but I wrote 0.75. Just then you have 29. So we could find force applied to point B in this direction. So it means for this component, bar OB, the force is going to apply in the opposite direction. So 1373 Newton applied to this point, meaning that this component is under compression. So we should check two things, buckling and yielding. To avoid the failure, then by doing that we can design the thickness of cross section. Factor of safety is 4. It means when 800 applied here, this bar should support 1373 Newton. But since the factor of safety is 4, we should design this bar such that P critical or the maximum force shouldn't exceed, should support this, which is 5492 Newton. So I should design this bar such that it can support 5492 Newton, not 1373, because of the factor of safety. This is how the factor of safety is affecting the problem. Good? Any questions so far? All right. Here you see I provided two values for C. C equals to 1 for in plane, buckling, and 1.2 for out of the plane. What do I mean by in plane? In plane means, if you look at this bar, and this is a cross section, means the buckling occurs about z-axis. So we are going to have something like this. If you apply the force, it's going to bend it in this direction. Out of plane means something like this, which occurs about y-axis. So we might have two buckling. So in plane buckling and out of plane buckling. And we should check both. I will start with in-plane buckling. Means rotation or buckling about z-axis. I don't know which criteria should I use. Should I use Euler criteria or should I use Johnson criteria? To do that, first I need to find L over K1, then check with L over K1 for this column and figure out which one should be applied. So let me calculate L over K1. For buckling, E is 207 gigapascal, C is 1 for in-plane, SY is 165 megapascal. I will find 157.4. So this is L over K 1. Now let me find L over K. What's the length of column? We are not given, but we are given with 900 and 500 millimeters. So L square would be a square root of 0.9 square plus 0.5 square, 1.03 meters. Pardon? Thank you. So L is 1.03. But what's the K? This is how I can find K. I'm talking about the in-plane buckling, means buckling about z-axis, so I should use the IZ. IZ would be, this is B, this is H. B times H cubic divided by 12. T times 25, let me use in the millimeter, then I change it to the meter, over 12. This is I. A is T times B. So K square would be I divided by A. I divided by K. By area, sorry. I divided by area. I has one term of T, area has one term of T. I can cancel them out. One of these 25 can be cancelled out with this 25. I will get K equals to, we just have numbers. So we can find K equals to 0.0078 72, sorry, meter. So I define this 0.0072. I will get 142.7. For in-plane buckling, L over K is 142. L over K is less than L over K1. Johnson. So this is greater than L over K. We are going to use this one. So left side, P critical over A. P critical should be this, 5492 divided by area, which is T times 25. SY is 165 megapascal. Megapascal means 10 power 6. Negative SY divided by 2 pi. L over K, I already have L over K, 142.7, both squared. 1 over C is 1, E is 207 gigapascal. Right side, everything is given. Left side, the only thing is not is unknown is thickness. So I'm writing the thickness would be 2.26 millimeter. T1. So for in-plane buckling, if you don't want to have in-plane buckling, the thickness should be greater than 2.26 millimeter. With this thickness, it can support fist force to avoid the in-plane buckling. So I'm done with just in-plane buckling. I still need to look at the out-of-plane buckling and the yielding. So I will get 2 more thickness. Any question on this? Everybody knows why did I multiply this by 4? The force that I calculated. Then I checked, I find L over K1. I calculate L over K, compare them. I concluded that we should use the Johnson criteria, plug in the numbers, find the thickness. And in-plane buckling means rotating about z-axis. If it's bending about z-axis, just imagine about z-axis. Out of plane means something like this. The C for that is 1.2 for out of plane, and IZ is gonna change to IY. So I'm gonna look at the out of plane. IZ is gonna change to IY. K should be calculated again because IZ has been changed. IZ is gonna change to IY. This is gonna get cubic, and IY is gonna be 25 times T cubic. So divided by 12. Area would be the same. K squared would be I divided by area, which is T cubic 25 divided by 12 divided by area. I can cancel out one of the T with this. It's going to be T squared. These 225 can be cancelled out. I will get T squared divided by 12. K would be T divided by S square root of 12. So here I will get T divided by S square root of 12. So the value that I will get is going to be 1.03 divided by 0.289 times T. It depends on the T. If you calculate L over K, here the only thing which is different than the previous case is C, because E is the same, pi squared SY would be the same. It's going to be 1.5. So 157.4 is going to change to something.
1.5 or 1.2?
1.2, thank you. Not 5. So times S square root of 1.2. So L over K, 1 is going to be this. 157 times S square root of 1.2. So if you compare with this, you cannot tell which criteria should be used. So you should assume, you should make an assumption. Suppose you're saying that we know that the Euler criteria is going to be valid and work with this. After you find the thickness, come back here and find L over K and check with L over K1 to make sure that your guess was right. If it wasn't, use the other criteria and calculate the thickness. So again, I cannot tell which criteria is valid, so I'm gonna say assume either Euler or Johnson. Assume Euler. So if I assume this, I'm gonna use this one. P critical 5492 divided by area 25 times T equals to C 1.2 pi square. E is 207 gigapascal divided by L over K square, which is this one. L over K. Yeah, L over K. That's 1.03 divided by T over S square root of 12 square. L over K square. L over K square. This T square goes up, multiplied by this T, it's going to be T cubic, and you will find the value for T. I'm not doing the steps, just write the value for T. T2 is going to be 10.45 millimeter. So I just skip the math. I have one T here. If this T squared, it goes up. If you multiply by this, you will get T cubic, and you can find the value for T. It's going to be 10.45 millimeter. So T1 was 2.26, T2 is 10.45. We are done with the buckling. I should check with the yielding. Yielding is sigma should be, we should set equals to SY. And sigma is P divided by area, which is 5492 divided by T times 25 millimeter equals to SY. SY is 165 10 power 6. You can find the thickness. T3 is going to be 1.33 millimeter. 165 times this equals to this one, solve for thickness. You will find T3. So if you want to avoid in-plane buckling, T1 should be, thickness should be greater than 2.26. If you want to avoid out-of-plane buckling, it should be greater than 10.46. And if you want to avoid against the yielding, it should be greater than 1.33. So we pick the maximum of T1, T2, and T3, which is 10.46 millimeters. So the thickness of this bar should be greater than 10.45. Yes.
So for the second one, the out of plane, we would just plug the T back in for L over K and then make sure that our assumption
Yes,
is
I
valid.
forgot to say that. I assume it's 10, it's going to be Euler. Now I should find L over K and compare it L over K1. So for this thickness, it's going to be 1.03 divided by 0.28, 9 times 10.45, 10 power negative 3. It's going to be 341.5. So 341.5 is definitely greater than this one. So 341 L over K is greater than L over K1. It means our guess was valid. I forgot to do that instead. Any question on this? All right. Let me just have a quick review on this problem, this example. There is a column that we would like to design. It's a round bar. So the column has a circular cross section. We would like this column supporting 22 kilonewton load. The length is 1.5 meter. Round bar, the force is 22 kilonewton. Compressive. It's made of the material with 500 megapascal yield strength and the modular elasticity of 207. Design the diameter of this column to support this load if the factor of safety is 4. So if the factor of safety was 1, or if we didn't talk about the factor of safety, the maximum load that this column should support was 22 kilonewton. But by considering this, P critical should be, we should design this column such that it can support 88 kilonewton load. So we should start with L over K1. Just plug in the numbers to find what would be L over K1. L over K1. It's a pin. So C is 1, pi square, E and SY are given. L over K1 is going to be 90.4. Find L over K. It's a circular cross section, so K squared would be I divided by A, pi d power 4 64 divided by pi d square divided by 4. This, it's gonna be d square divided by 16. K would be d over 4. So L over K 1.5 divided by d over 4, or 6 divided by d. But we don't know what would be the d because we are going to find d. So we cannot compare this one with 90. Assume either Johnson or Euler. I assume Euler. I assume Euler criteria, which is this one. Peak elliptical is 88 kilonewton. Area is pi d squared divided by 4. C is given, pi squared E, L over K is a function of D. We solve for D. So we find D equals to 37.48 millimeter. Come back and check L over K. We will get L over K 6 divided by 37.8 times 10 power negative 3, 151. It's greater than 90. Euler should be used, and we use the Euler, so we are good. We know, I mean, the next part is saying that we should use the preferred size. Preferred size, the closest number to 37 is 40 millimeters. So the column should have the diameter of 40 millimeters to support 88 kilonewton force. We can check against the yielding, but it's not going to be valid because Euler is going to be here, so SY is going to be right here. So the bottom is going to occur first. But if you want, you can check the yielding as well. All right, I will stop here.